All right, hello. Let me just find that proper window. There we go. Okay, so yesterday I did a video where I went into the current weird graph on the Schumann Resonance chart on the space observing system of the website of Tomsk University in Russia. And I tried a very simple method of converting it into sound, going from the image. And today I'd like to do a more advanced version. So I'll just take it step by step, take you guys with me, and we'll see where we end up. Okay, so first we need to extract that image here, which we can't do just by right-clicking. We could take a screenshot, but it'd be a low quality version, so I'll just pull it out of here. We go inspect, right-click inspect. We see this P element here. Here's the image. Right-click on the image, open a new tab. Here we have the image. Copy that to the clipboard and open GIMP. Where's my GIMP? There we go. Open a GIMP. Takes a second to load. There we go. Oh, I can't see the image. No, not that one. That one. There we go. Okay, great. So pasting in that image, and what we want to do is we crop out that image. Like yesterday, we go just right after hour 20, and we stay within the data range like that. So this is our crop. We save it as a TIFF file because we will use Audacity later to import it, and we want that TIFF file format. So we go to export as, we choose TIFF as file type. And then when we hit export, it will pop up a dialog. And now let me check which one it is. Okay, so we want to have TIFF with the following settings. Image compression, none. Pixel order, interleaved. And byte order, IBM PC. Okay. I can't really do that except choosing compression none in GIMP. So what I will do instead is find some online website that can do that. Anyway, we have the image file now. Let me just find the... Okay, there we go. Also, this is the website I'm using for instructions. So let me find a TIFF converter, something similar. Okay. There we go. That looks good. Okay. Find my TIFF file. Okay, great. Try that one. Oh, doesn't work. That's great. Okay. Okay, we'll try it anyway before I go crazy here on trying to solve a problem that does not even exist. Okay, so we have our image, cropped it out, exported it to TIFF. Now we go to Audacity and following that instructions, switch that window. There we go. So let's see what we need to do. Okay, open Audacity, choose file, create new project. Yeah, I got a new project. Okay, had one before. Save project as to save and name the project. Yeah, obviously. Okay, file import raw data and raw data, and then we choose the TIFF file. Okay, let's do that. Now there's some settings we need to follow. Encoding is U-law, byte order is big endian, channels is one channel mono, start offset 0 bytes, amount to import 100%, sample rate 44,100. Okay, importing. Great, now we have imported it. Let's see how that sounds. Wow. That sounds terrible. Let's see how that looks on the spectrograph. Have not worked with Audacity in a while, so I'm kind of trying to find my way around this. Right. Well, I'm not sure that actually worked because we really need to see the spectrograph so we can check back if what we came out with and put it through a spectrograph again if it actually looks like the spectrograph that we started with, right? So I don't know why that plot spectrum doesn't do anything here. Oh, wait, I think I get it. Yeah, there's the spectrum. Okay, here we go. Yeah, that is the spectrum, but it is it's not an overtime. It's just a histogram. So it does make sense, but let's dial it down a bit. So here we can see this is our biggest spike, and that is 17 hertz. Second biggest spike is at 500. I don't know, 525. Okay, so that was that was very rough because I didn't actually set any parameters of where's my where's my top range, where's my minimum range. Okay, so that clearly wasn't it. Let's just see what else is out there. So basically Google Sonification to see if we can't do anything. We end up with a bunch of glitch art. I'm not interested in glitch art. I want to reproduce a spectrograph, a spectrogram. Okay, apparently sonification usually means you take some visual data, whatever it is, turn it into sound. And it's turning a spectrogram, or I have to Google if that is actually a spectrogram or a spectrograph. It's driving me nuts. Okay, so a spectrograph is the device. Okay, makes sense. And a spectrogram is a visual representation of the. Okay, so I'm talking about the spectrogram. Sorry for the confusion. So, right, so this is what I'm talking about. Sonification of a spectrogram needs careful consideration of the upper and lower bounds and what frequencies they will be mapped to. Obviously, but yeah, I'm a total newbie at this, so bear with me. Okay, so let's see what the Redditors have to say. Oh, great. Reddit is closed. Awesome. Don't you love censorship? Spectrogram player. There we go. Okay. So this is the one I was already using. but it wasn't too helpful. That's this one. So already using that. Well, we can do one more thing. Yesterday I realized I had it switched upside down. So I had the low frequency part at the top, or not me anyway, but the Tomsk Observatory. And usually the convention is that in a spectrogram, the low frequency part is at the bottom. So it's basically not playing correctly. So to play this correctly, not accurately, but correctly, would be like this. I was just playing around with it earlier. Doesn't sound much different. It's just sounds a little bit different. Okay, let's see. I mean, the problem I have with this really is these massive artifacts we can see here, because all of this is over the span of several hours, and it's a spectrogram is fairly low resolution already in principle. It's not meant to be reverse engineered. If if you attempt to reverse engineer a spectrogram, you already know it will be very low accuracy. So unfortunately, can't get around that. But I was hoping we could get at least these colors mapped. So right now it looks like black and white, even though I say grayscale here. This is just the way the visual player displays. It doesn't do anything for actually mapping the colors. So it doesn't increase the dynamic of the mapping. So grayscale is 265 values per pixel. And color is, well, normally this kind of color is 16 million per pixel. So it's a lot more dynamic. And we would have a lot less of a rough sound, less, well, a lot less rough anyway. I'm wondering what can we do to get more resolution in this. It's called an inverse spectrogram. That's awesome. Great. Okay, we can go with that. So, wow, what? Holy shit. So, okay, so that's what we just heard, and this is the image to that. Great. Okay, and this one, this guy sounds like this. Yeah, that's nice. but okay, sound and image, great. So Wolfram Alpha, supposedly this is an example. All right, let's just copy this to clipboard. Actually, this. And we go to Wolfram Alpha. I hope it's still free. Almost got me through university. Not quite, but you know. Well, I always hated that it really gives you a bunch of useless option. Doesn't really help you at all. Well, I know my sample rate. But look. So it looks like it can only do grayscale. Okay, not a problem. We'll just grayscale the image to preserve the dynamic. Not a problem. I will do that online. That's the one. Grayscaled image. Yep. So black is silence and white is not silence. So go with PNG. All right, got that. Now we try inverse spectrogram image. Okay. Yep, that one. Oh, what? Okay. Well, see what I mean. Wolfram Alpha, you're just absolutely useless. This is your reference. Why can't I just copy to clipboard and paste it here? And then it just works, you know? Wouldn't that be nice? No. I have to debug it. I don't know how the site is still around. Worst usability ever. Maybe we need to tell it math input. I don't know. Let's try it. Well, that's no fun. Examples, alright. Play. Yeah, great. Direct link to example. What? Let's do it. Unbelievable. Unbelievable. Yeah, I get it, but yeah, unbelievable. Absolutely unfucking believable. So I in inverse spectrogram. Okay, let's just type it, right? In brackets 1 colon equals. Sure, I can do that. In bracket 1 colon equals. And then we go inverse spectrogram bracket image. Is that capital? And okay, it's audio. Comment here. The fuck? Yeah, yeah, great. And it doesn't understand my query. Of course not. I don't even understand it. Hey gamer. Well, I'm trying to convert the weird Schumann Resonance chart that popped up yesterday. Well, it was kind of, people were talking about it. I'm trying to convert it to sound. Using whatever I can find in a quick Google search. I was using this thing yesterday, but it's a little bit low accuracy. But anyway, it sounds like this. I know, not too exciting, right? So let's try like this. Inverse. We just learned a new name, so we'll use that. Spectrogram. Yeah, this looks good. That looks very good. Oh, that's Python code. Not too. I'm not too confident in my Python. I was looking to find some kind of workbook where I can just put the image in. That'd be great. But this is all Python code. Let's check Stack Overflow. Okay, so this guy says it's not possible because of the way the spectrogram is calculated. So he's saying you lose any phase information because you throw away half of the, basically you throw away the negative amplitude phase. If you look at the audio wave, you only keep the top half. And he says it makes it impossible to accurately reconstruct the original time domain signal, which is the waveform. So, but he says it is it is possible to reconstruct a signal that sounds approximately the same. Well, that's good enough for us. So let's keep going. Okay, no solution here, but we learned something. Apparently, there's a MATLAB plugin called Inspectgram, but I don't have MATLAB, so I'm still looking for some kind of workbook where someone already did the work. You know, trying to do it the lazy way. Let's check this out. For some reason, for AI, people love Google Colab and Google Work, notebooks, but maybe this is just not a popular topic. Maybe after June 18, 2023, it will be. However, I can't imagine I'm the only one who wants to hear this weird graph that appeared yesterday on the Tomsk Observatory. Hmm. Okay, that's a bunch of paper, bunch of math. Well, I'm not interested in the accuracy. I'm just looking for an approximation. So, hmm. Yeah, potential applications. That's great. Mm-hmm, mm-hmm, mm-hmm. Inverse Fourier transforms. Great. Now I'm deep in the theory. Man. Okay. Well, yesterday I turned to ChatGPT for answers, and it had some answers, but not not great answers. All right. So first need to prime it. Let's choose GPT-4. Okay. So we prime it. So, it acts in a constructive way and not just gives me some guideline and bullshit. I'm not jailbreaking it because I don't want it to give me made up answers. All right, let's see. Okay, it's giving me the full theory. Yep, inverse short time Fourier transform, then windowing, then overlap add method. And then the devil's advocate comes in and says there's caveats. Yes, missing phase information, we learned that earlier. You can only make an educated guess at the original sound. That's fine. We will lose timbre and quality. That's fine since we approximate 32 hours into whatever 5 minutes. We don't care about timbre and quality at all. Yeah, might be different. That's fine. Yeah. Okay, great. So how can we do this easily? Python, yeah, great. Not doing that. MATLAB. Well, I'm not doing that. Don't have MATLAB available. Okay. Librosa. So it's telling me Librosa is another Python library and Sonic Visualizer. Oh, awesome. It has the functionality to do that. Let's try that. Perfect. Oh, wow. Free and open source. Amazing. Love it. Oh, I tried that yesterday and it wouldn't download. I remember. Okay, let's try it again. Work this time. Yep, except. Okay. Maybe we should have just turned my computer off and on again yesterday. And already would have been here, but never mind. You don't know that in the past. Okay. There we go. Got all the images ready and got got everything prepared. Okay. All right, let me switch over the window. There we go. I don't know how do you do that. Open. Well, actually, I first need to figure out how to do that with Sonic Visualizer. All right, asking ChatGPT again. There we go. What? It just told me it can do it. Reverse a spectrogram. Ah, great. Well, thanks, ChatGPT. Just trolling me again here. We'll try it anyway. We'll figure it out. So transform, whatever is this. I'll just okay. Standard files. Oh, convert audio from data file. That's interesting, but it's CSV lab and text files. No, we have an image, so that's different. Oh. Hmm. Doesn't really look like you can do that. I don't think it actually can do this. Let's go back to ChatGPT. Oh, there we go. So photo sounder seems to be available. Let's check it out. Nice. Okay. Previous releases. Yeah, I'm fine with previous releases. Of course. No, it's a demo. Okay, see where we can go with this. Sure. Okay, Sonic Visualizer didn't work, so let's do Photo Sounder. All right. Open the image. So, okay, let me switch over to that other app. There we go. Okay, so this is our spectrogram. Let's load it. Okay, there we go. Let's hear it. I don't hear anything. That's great. I mean, that's pretty good. Now, I mean, we should probably adjust the range here because the original range wasn't 20 kilohertz. So let's see if we can do that. Also, we need to set the audio output device. Mm-hmm. Wow. Holy shit. That is absolutely scary. Wow. That felt so bad. That that's how I imagine, you know, the the winds of hell blowing through the lonely, fiery plains of the underworld. Yeah, listen to this. Oh man. Can you imagine someone calling this the sacred geometry of the fifth dimension ascension, blah blah? Incredible. These people see three colors in one place and they think they just saw God. Incredible. What's what's sacred about this? And especially there's no geometry in here. It's just fucking curves. There's no geometry. There's no straight line at all. I don't think people understand what geometry even means, much less what sacred even means. Sacred just means in harmony, balanced, and in harmonic ratios. So that's basically what it means: harmonic, balanced, and well, these might have the same distances to each other. I'm not exactly sure that they are harmonic. At least they're not harmonic with biological life. I don't think so. I mean, I haven't checked, but on first sight, it doesn't really seem likely. We got someone in the chat. Okay, listen to this. What do you think? I mean, yeah, I don't want to say either way. So I'm just trying to get to a place where we can actually listen to it, and maybe maybe there's nothing concrete to find here, but I want to try anyway. So next step, I want to go and go back to where we were at the beginning, which is at the Tomsk Observatory. So let's go back here. So as you can see, this is the full image. As you can see, we go from 0 to 40 hertz. Yeah, that's a good point, but that doesn't mean it is natural, right? I know, like, there's this thing called sleep paralysis, and so you can hear a crackling sound or a loud boom before you fall asleep, and people say that's like your mind slowing down or speeding up or whatever, and so ambient noises suddenly become very slow or very loud. Things just go out of whack. Well, well, your consciousness transition into the sleep state. So yes, that that is a thing, but that just means you hear weird sounds while you fall asleep. It doesn't mean there's anything sacred or holy or whatever about it. It's just a natural process. Now, then that also means it will sound similar to when you hear weird sounds while you're awake, like this stuff. That doesn't make this anything holy or sacred either. It just means it sounds just as weird as the stuff when you fall asleep. But um, you know, that that doesn't really tell us either way. So it is an interesting observation, though. Okay, so I want to just calibrate this image. So now we see here 0 to 40 hertz, and I want to try if I can pull this down to 0 to 40 hertz in the app, the photo sounder, and then expand it. You know, so we got the octaves right, because the octaves right now are in the megahertz, um, and to make it audible and hit the right musical notes, we need to follow the right process. So until now, I've just been very rough with it and just kind of thrown it in there to so we hear anything at all. But I want to be more precise now, because remember, this is electromagnetic radiation. You usually don't hear this at all because we don't have antenna for ears. We have ears who react to uh, vibrations in the air and not to vibrations in the electromagnetic spectrum, which just means air vibrates at, I mean, what we can hear is between like 50 vibrations per second and let's see, 15,000 vibrations per second. And this stuff vibrates from pretty much oh, uh, from 0 vibrations per second to 30. But in the electromagnetic, so basically what the Schumann resonance is, what they're measuring is lightning. It's lightning across the globe. So normally, but I mean, of course, this is probably not lightning, but some kind of technology that someone turned on, and so some people had suggested that it might be the Large Hadron Collider. So let's see. Let's see what we can do with this program. Harmonics. Okay, so we want to kind of we want to scale. Wonder how we can do that. Normalize, no. Vertical normalization, I think. Okay. This is, I think, similar to the black point thing in Photoshop. Let's do horizontal normalization. Oh, now we just have more noise. Let's go back on that. Oh my god, it just has one undo. Well, that's weird. Okay. Well, that wasn't it. That sounds like a organ from hell. Okay, well, it's not Photoshop for audio. Let's see what we can do. Pixels per second, time resolution. Frequency scale. Oh, that looks good. Okay, max frequency. Here we go. So we want to do 30 hertz. Yes, that's what we. It's perfect. It's perfect. So let's do this. What is 30? Yes. Now, of course, we can't hear anything anymore. Minimum frequency is 0. Yeah, so we can hear anything. Frequency scale. But this is, okay, so this is the accurate frequency scale. Now we should be able to double it. So now we can do 60. Wait, let's go slowly here. Pixel per second time resolution. It's 200, 200. So I will just try to go in doubles. Okay, it doesn't do anything, not yet. So first we need to double the frequency's resolution. So we go to 30 max hertz to 60. And then let's just go to 120 because that's twice. Can't really hit that. Come on. No. Okay. 120. Come on. Okay, we're deep rambling. We keep on doubling. So 120, 240. We'll do 480. All right. Maybe we can hit that. Let's see what's next. 480 times 2. That's 960. Can we hit that? No. 978. Listen to that. Okay. So what I'm doing is I went down to 30 hertz, which is the original as I shown you. Well, so Mundo Dasa, well, I'm trying to find, I don't know what I'm trying to find. I'm just trying to find something, right? Just playing around with it because just looking at the graph wasn't really enough for me. So I was trying to hear something, right? And so I went down to the 30 hertz, which is the original scale of the graph. And now I'm doubling it, which means we will hear the octaves, but we will keep the original structure of the image and of all the patterns in it intact. So if we just double it, we'll keep the information true, so to speak, as best as we can. So 960, double it again. It's 1920. 1920. That's okay. 1926. All right, not sure. Let's go one more. Double it again is 3,840. I wish I could input that manually, but I can't really. Oh, here's a pixel spray width. Maybe we can play with this. If I reduce that, maybe we get a better resolution. Okay, first let's hear that. Okay, so we're getting close to so 4 kilohertz is like the the center of the frequency where most speech appears, or like, frequency of speech. So if we are around 4,000, that's where you would hear something if someone had put in voices. But I'm not saying there's voices in there. I'm just saying this is why at this frequency we're at now, it will sound familiar because your ear is used to hearing frequency that are familiar at this frequency. So if we go one more double, we will be right where you will be very familiar with these frequencies, I mean your ear, and it will be very easy to hear things even if they are not there. So let's try that. Double that again, and we are at 7,680 Hertz. Yeah, we can't really hit that. We can get at 7737. Yeah, question in the chat. Mundodasa asking, when has it changed? So yesterday at 2 p.m. UTC, the Tomsk Observatory in Russia, who is usually showing the official Schumann's resonance graph, had a blackout gap of like roughly 2 hours, and then the normal Schumann display changed from what it normally shows to this, and everyone freaked out and lost their mind because this is very unusual looking. So I'm just trying to dig a bit into this. Okay, let's see if we can get more clarity here. Some of these knobs. Okay, so I can slow it down from, we were from 100, we can go to 50. All right. Okay. And then here we have pixel spray width, so maybe, I don't know what that is, let's try it. All right, I guess that's just a tool if you wanted to spray paint on the image. Yeah, I saw a contact too. Well, sorry, but I wouldn't know how to fold and roll that. If you have any hints on how to do that, let me know, put it in the chat. Like in the movie Contact, maybe that's what you're referring to. They received a bunch of 2D images, and eventually they figured out that these all have certain keys on their corners, certain symbols. And so they figured out that it was a blueprint, but a 3D blueprint that had to be assembled according to these symbols on the borders. And so when they assembled it, it turned out to be a big machine that acted like a portal. So yeah, right. I mean, they put this movie out. They put this thing out. Of course, people have that association, but you got to remember it's pretty much coming from the same source. If you get down to it, so I'd rather try to do my own research first before I go down that rabbit hole. Let's see, what is vision mode? Well, looks better. we can play it faster too. Let's do 200. I don't know, let's do 400. Well, it seems too fast. Not really sure. 200. 200 seems alright. Still doesn't sound like speech. Well, let's do double it again. And we end up at 15,360. Oh, that's very close. So we had 15,377. Oh, okay, there's an idea. So you're saying if I try to put one line at a time. Yeah, we could do that. Okay, let me save that. Okay, let me save that one first. And we'll remember to go to that number 15,360 and 200 pixels per second. Yeah, well, it's not waveforms, it's a spectrograph. Sorry, spectrogram. So this if you're thinking in waveforms, this is way too rough. You can't make a waveform out of this. This will just sound like someone farting or burping. We can try it, but don't get your hopes up. And we can use the other tool for that. That is easy stuff. Let's do it in the other tool. Wait, let me switch you guys over. Wait, where are you guys? I think here. No. Come on, OBS, do your job. There we go. Okay, so we can do the bottom line. Let's do this, right? Okay. It's already done. Oh, okay, it's already done. Let's go. Yeah, so as you can see, that one is not very interesting. We can move it up, go to the next one, just clip it right about here. Maybe we have to, sorry, I thought, so for this exercise we have to really limit the frequency. So it's limited to 10,000. Yep, there's your fart. Yeah, well, you're right. It's a sped up fart. Yeah. Um, let's see. We could take this. We could take this into the photo sounder to see what this sounds like. Yeah, it definitely sounds like something that needs more sound processing, which I'm not really able to. It sounds like something that is more complex. It could be 3D waves. It could be something that's encoded. We have some interesting structures here. If you look at these, points here where things cross over, you could probably calculate some things from the angular relationships between these lines and then extrapolate some 3D stuff, which I'm absolutely unable to. But yeah, there's some regularity here, and then over here as well. And there's something here that looks like regular structure. This one. This stuff here in between looks more, it's either more complex, in the graph didn't really capture its intricacies, or it's just, well, I don't know. I mean, it all looks like it's much more complex than what the graph can show, that's for sure. So, we're working already with a rough copy, and we're working with rough methods on a rough copy. So it's really more playing around than doing analysis. But like I said in my video yesterday, I really want to just inspire someone with more technical ability to get inspired and look more into this. Yeah, it's too complex for a malfunction, don't you think? I mean, what kind of malfunction looks like a hippie screensaver? I don't know. Definitely crazy stuff. This is the current live graph. So it's still ongoing. Check this out. We can actually pull a fresh image in here. Let's see. This is from the current data. Come here. You get out of the way. So, like that. Save it. Okay, and then flip it. Oh, no. Like that. Flip it again. Yep. Wait, no. No, it's wrong. Now just flip it horizontally again. No. No, wait. It's not flipping it. Just vertically, please. Okay. Okay, let's load the latest. We can just kind of listen to this one. That was the 10 kilohertz capped one. We can listen to the full thing as well. I mean, starting to sound like some alien whales, don't you think? Let me make that a little bit smaller. Let's take 3 of these cabbage things here. I can definitely start to hear him talking to us now. Yeah, absolutely. I can hear it. Let's make that 10 seconds, like double it, right? So I don't know what language that is, but some language for sure. Let's double it again. Right. Yeah, we came from 20 seconds. So if we slow that down half, it was like this. Also, maybe let's try one cabbage here. So we have one of these. So we have more. Let's just see how that sounds. So let's go to the 20 seconds again. Yeah, that's not very intriguing. Well, welcome to the chat, Listen Turner. The thing is, this is a 32-hour or even more at this point. Let's see how much is that actually. So let's see, that's like 15. Okay, it's 15 from here, 15 and a half. And that's 24 and 15, that's 19, 29, 39 here, 41, 2, 3, 4, 5. So 45 hours. Right, so it's 45 hours, the length of this thing. So yes, it is ELF, but I'm kind of trying to find something that's probably not even there. Right, so what do you suggest? What do you want me to slice? I'm looking at vertical. Remember, this is the spectrogram. So this frequency is over time domain. Top is high frequency, 20,000 kilohertz. Sorry, 20 kilohertz, and bottom is 0 hertz. So if we listen like this, make it way slow. I can't make it slower than this. So this is the slowest. Check this out. This is the full thing. 20 seconds, but it's still 45 hours and 20 seconds. It's still Well, it sounds like this. Okay. Well, the most dynamic range would be very thin line. Thing is, let's take this one and this white line here, something like this, right? See what happens. Well, let's go back to the photo sounder, because I don't think this is really too great for this task. Let's see. Change the window. There you go. Okay. So we were using the so I went way down to 30 hertz for everyone new in the chat, and then I doubled the frequency. So the original is 0 to 30 hertz. So I scaled it way down. So the top of the scale is 30 hertz, right? Like this. This is the original graph. Electromagnetic, not audio, but still the harmonics and the structures are intact. Well, the thing is, the diagram is way too low resolution to take a 60-second slice. Because, look at it. Look at it, man. It's full of artifacts. It's just super crappy diagram. Yeah, well, there is a repeating message, but it doesn't look constant. You have this thing here, if you can see this. This looks like where it starts, and then it goes into this, and there's another concentration point, and then you have this. It reminds me of a corn circle, you know. It looks like a corn circle to me, but in the frequency domain. So I don't know how corn circles are made in terms of the translation to frequencies, to 3D space or 2D space, but I can imagine there's resonance involved. So maybe this is like a similar thing, who knows? And that, that's not an answer to anything, but oh yeah, crop circle. Yeah. I'm not a native speaker either, so sorry about that. Crop circle, absolutely. So it reminds me of a crop circle in that you see repeating patterns, but you don't quite get the meaning. But it's clearly a pattern, and it's clearly not random, right? It has these aspects of a crop circle. Okay, so I wanted to double this again, so let's go to 30K. Oh, I can go to 26K only, okay. Divide by 2 again. So our max is 15,360. That's fine. That's like this, 381. Yeah, sounds like this. Right, let me slow it down. Okay, here I can slow it down. So this is half pace at 50. let's make it slower, 25. Well, guys, the thing is, if you take half a line or one line, it doesn't, it's frequency domain. Yeah, well, I wish there was. I wish there was. AJ is saying perhaps there's an AI tool. Well, that's where I went first, but there's only AI tools for things that people are interested in. Yeah, there's not even a lot of manual tools for this stuff. Mostly there's just scientists writing papers about it with a bunch of math formulas and some Python script. So usually people write AI tools for stuff that's out there as an app so they can compete with it and take a market share. So let's listen to this 25. This is like 25% slowed down. This stuff definitely looks like 3D. It reminds me of a basket weaving thing, or if if you have a bunch of poles, bind them together and stand them up like this, like Mikado. Now if we slow it even more, it's 12.5. Well, it is phasing because there's a lot of stuff happening at the same time. Let me see if I can do a selection. That would be interesting. And just play that. No, can't do that. What's that? What is that? Oh shit. Oh, this is making it quieter. Well, the Gothic topic is asking, is it possible to translate the wave to binary? Well, first of all, we started with a crappy ass spectrogram as an image, JPEG, lots of artifacts. I'm trying to turn that into a waveform, which will have tons of artifacts. Turning that into binary, you might as well record the wind outside of your house. If you want to find anything in there, you might have more luck doing it like that because it will not retain any accurate information. The most that you can do is to quantitative analysis, looking for larger trends and stuff like that. But you can't really see discrete values because of all the process this has gone through, I'd say. So I thought this was the best bet, like looking at this and then hearing patterns maybe or seeing patterns. I can try to keep slowing it down. So Turner is saying slow it down more. 6, going down to 5. Yeah, we can make an horizontal slice. Let me do that. I need to go into GIMP to do that. Just cut it up. The tool itself can't do it. Okay. So, what kind of slice are you thinking? If you're looking here on the left, you have frequency markers, right? Just tell me from one marker to some other marker to cut it, like roughly. Tell me a frequency here. and we'll slice it according to that. Or you can go here on the right, you have the C scale. Yeah, that's a good point. Since this was posted publicly, there's probably something in there. But on the other hand, it's been known for a long time that the members of the intelligence community use publicly available channels like newspapers to encode their messages, just so they don't have to rely on expensive infrastructure. So just because a message is public doesn't mean it is meant for the public. Well, most of the time, it's probably not. Yeah, I do see that, but they're also interwoven. So if you look at this crossover point, or let's say this crossover point, it goes down here, 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 right? And it probably doesn't stop. So it's like a mesh. So if I cut it off here, who's to say that it's not meant to belong together? The one in the middle. Okay, let's do that. So let me switch over here. One sec. Go over to GIMP. Okay. So I'm gonna crop this. How about something like this? Maybe like this. How about that? Just like 2 lines so we capture the overlap. Does that look good? Or we could just do one like this. Let's do one and see what happens. All right, do one. Exporting, keep that open. Okay, let me switch back to that app and we open the new file. I mean, good thing now I know the process, so now the rest is easy. Can do that all day now. Wait, look, this is what one line looks like. Okay. Yeah, sorry, chat is a bit delayed, so I just saw that feedback. Okay, let's hear that. Now, if you look at the waveform now, it looks way more interesting, right? And so let's slow that down to, well, let's start with 100%, just so we have a reference. Yeah, that sounds terrible, of course. Sounds like this. Oh wait, we have to go to the normal scale of 20 kilohertz first. Just for reference, you know. Wow, we don't hear anything. What the hell? Oh, okay. Oh, it's because I don't know why actually. Now, wait, now we have to calibrate this first. So, wait. I completely confused this thing now. So, wait, so first we go here. Switching over. No, that's the wrong one, sorry. This one? No. Oh man, the streaming thing. Here we go. So we went ahead and captured this one to this one roughly. So that's roughly from 23 to, let's say, 17. Yeah, let's say 18 to 23. hertz. Let's do that. Well, you know, there's so many parameters, 18 to 23. We can do all kinds of things, but we'll just start slowly getting there. So I'll do this 18 to 23 hertz because that's what it looks like on the original. Of course, we can't hear anything at that frequency, so we have to double it. Yeah, so we do, let's stretch it a bit and we say 20 to 30. So we do 40 to 60. Right. Come on. It's lagging. Great. You hear that? Now it's getting interesting. I'll slow it down in a minute. 80 to 120. By the way, I have to end the stream in a minute. I'll continue probably later today, but I gotta end this very soon. This is doubled. You can see how this low resolution of the image really shows, or, you know, it's really, really crappy resolution. Double it again, 160 to 240. You know, that's starting to sound interesting. 320 to 580. Yeah, there we go. 80. Come on, 580. Here. Okay, now I can slow it down, but I have to stop the stream. So, to be continued. Thanks for joining in, guys. Sorry to cut this short, but I got an appointment. All right. To be continued later on. Have a good evening. Bye.